thing we want to mention is phase changes. So when something is going from a solid to a liquid, or vice versa, from a liquid to a gas, or the other way, those are phase changes. An interesting thing happens when you take a liquid, like water, and you get it to evaporate. You get it to boil. That's a phase change that's taking place there. One of the things that happens is that the liquid gets colder. Why is that? Because I've been throwing out this term, the average kinetic energy. What does temperature tell us? The average kinetic energy of the molecules. That means that there's some distribution. So if we look at the number of molecules, and we look at the kinetic energy, most of the molecules have a kinetic energy that's about this average value. And the temperature tells us what that value is. But some of the molecules are much hotter, moving much faster. Some are much slower. It's just an average. Most of them are at that energy. Most of them have that kind of much energy of motion, vibration, kinetic energy. So the analogy I like to use is you take the height of every person at the school. You'd get a curve that looks something like this, right? Most people are the average height. Some are really tall, some are really short. So what would happen to the average height of the school if all the tall people graduated? If all the tall people graduate, the average comes down, right? We just lost all the tall ones. Well, which ones leave when we have evaporation? Evaporation, the molecules are moving so fast they can't hold on to each other anymore and they become a gas. The ones that are moving really, really fast are the ones that are most likely to move a little bit faster so they can't hold on to each other and become gas molecules. So the ones that leave, the ones that evaporate first, are the fastest moving molecules. Maybe they have a collision with another molecule, get a little bit more energy, and leave, and the molecule they collided with loses a little bit of energy. So the fastest ones leave. They also take a little bit of energy with it, so the average comes down. So we say evaporation is a cooling process. The average temperature of the liquid that's left behind is less because of evaporation. Some people use this to actually keep things cool. If you have something that you want to keep a little bit cooler than room temperature, you throw a wet rag over it. And as the water evaporates off that rag, it'll keep it a little bit cooler. It'll keep it, you can maybe get it about 5 degrees below room temperature by doing that. It's quite effective. The other thing is condensation. When you go the other direction, what happens? When the moisture in the air condenses, the water is gaining stuff because it's gaining at the high end here, right? The stuff that's in the air is high energy. It loses a little bit of energy and becomes water or liquid, and it typically comes in at the higher end. So your water temperature would go up as you have condensation taking place. So this is something that we're familiar with. What did you do this morning when you took your shower? You finish your shower, you turn the water off. It's winter time now here, so I know what I did. I cracked my shower door open just a little bit, just enough to reach my arm out and grab the towel and bring it back in and slam the door shut. And I dried off inside the shower. Why did I do that? Because inside the shower stall, there's a very high humidity, so the amount of evaporation is small, right? This direction is small because I've got a lot of humidity in there. It doesn't want to go in this direction. and the condensation is high, right? If there's all that moisture in the air, it wants to condense on me. And condensing is a warming process, right? And evaporation is a cooling process. So I've limited the amount of evaporation, maximized the amount of condensation, and I dry off in there as best I can so I don't get cold. But what's the drawback to this? There's lots of condensation and no evaporation, so it's hard to really get dry. So eventually you have to step outside the shower to finish the job so you can really dry off thoroughly. But this is something that we have a feel for already. Evaporation, condensation, warming processes, cooling processes. The other thing that we saw was that there's a temperature. I talked about this condensation taking place on a cold glass. Well, I did the demonstration with the graham cracker, and not only was I showing that I could keep that graham cracker in my mouth for a good bit of time, as long as I kind of moved it around, it didn't hurt me. But what happened to my breath? It condensed, right? I took a deep breath in over that cold graham cracker, and it brought a little bit the moisture. There's a lot of moisture in my breath. The moisture, the temperature came down. Those moisture molecules moved a little slower. The water molecules, they could grab onto each other and form a little cloud, a little condensation cloud as I exhaled. So another example of condensation, water molecules going from the gas state to the liquid state. Let's talk a little bit about specific heat. One more topic here I want to touch on. This is another thing that maybe we've had a little example, a practical experience with, especially if you like to cook. You'll know that if you take a metal frying pan, put it on the range, put the flame on there, you try to touch it. It's just a short time. You try to touch it, it's hot, right? You can't touch it. But if it has some water in it, and you heat it up like that, you can still touch it after a little bit of time. So we put heat into the metal changes its temperature very quickly. You put the same amount of heat into some water, the water doesn't change its temperature as quickly. Why is that? Something called specific heat. Specific heat tells us how much energy we have to put into a substance to change its temperature. And the idea here is that some molecules can absorb energy in different ways, right? The molecule can actually move faster, translate from one place to another faster. Its kinetic energy can go up. Or if it's a kind of a complicated molecule, maybe it can spin. Maybe it can vibrate. There are all different modes that some molecules can absorb energy. And not all of those convert to the temperature of the substance going up. So you put energy into something, if the molecules move in such a way that the temperature goes up, we get a temperature increase. So we put a little bit of energy in, we get a temperature increase. But something like water can absorb energy in a bunch of different ways, so that you have to put a lot of energy in to get its temperature to rise by a little bit. So we say it has a high specific heat capacity. And how do we figure that out? We use Q for heat. And we say, how much heat do we have to put into a substance to change its temperature? What would it depend on? Well, the first thing it would depend on, I just said, was the substance, right? So that's C. We use C for specific heat capacity. What else might it depend on? How much of the substance we want to change the temperature of, right? If we just have a little bit of water, we can put in a little bit of energy and change its temperature. If we have a lot of water, we have to put in a lot of energy. This is heat. Energy, right? And the last thing it depends on is how much we want to change the temperature. If we want to change the temperature a lot, we've got to put a lot of heat in. So this helps us figure out, that's mass, and temperature change. So we can figure out now how much heat we put into something to change its temperature, or how much heat we get out, right? If as my 90-degree water cools down to 20 degrees C, I can figure out how much heat I would get out as it cools down. I could figure out how much heat I have to put in to raise the temperature up. So this helps us with that. And then the other thing that takes place is it takes energy to change the phase of something. We've talked about that already a little bit. So for a phase change, Q is going to equal the mass times the latent heat. And it depends whether we are causing the material to go from a liquid to a solid, solid to liquid. That interface has what we call a latent heat of fusion. Or whether we're causing it to go from a liquid to a gas or a gas to a liquid, that has a latent heat of vaporization. You look those up in a table. And Q would either be positive or negative. Anytime we're putting heat in, Q is positive. So when would we be putting heat in? I guess I should put a plus or minus sign here. We would be putting heat in if we're taking something from a solid to a liquid, right? We would want to melt it. We would put heat in to change it from a solid to a liquid. So Q would be positive. If we're changing it from a liquid to a solid, we would have to extract some heat, remove the heat, so Q would be negative. And the same is true up here. Q is positive when the heat's going in and negative when the heat's coming out, but it's self-correcting because there's a temperature, delta T there. And remember, delta is always final minus initial. So if the temperature is rising, you end up at a higher T than you start. Delta T is positive, Q is positive. You have to put heat in to get something's temperature to go up. If the final temperature is lower, then delta T is negative and Q is negative. So that one's self-correcting, but the lower one here, when you have a phase change, you have to remember which Q it is. And the reason this is important is that we can then look at more complicated systems. What happens when we mix some hot water with some ice, with some metal at a different temperature, and we throw them all into a container, and we want to know what the final state of the system is? Well, we can figure that out with these equations.